Welcome to exam race. This is the classical mechanics and we are doing the periodic motion and the subtopic that is the normal modes. We have studied already what are the normal modes and we are here to solve the problems regarding this. So here we have two different masses 3m and m, and a spring is there attached in such a way that both have spring constant k and one over another. So we have to find the frequency using the small oscillations. So for this, first thing is to find degree of freedom. So its degree of freedom is obviously 2. Why? Because this is displaced led by y1 and this by y2. Then we can say there's a 2 degree of freedom. Clear? Now, so by using this degree of freedom, I already defined the generalized coordinate as y1 and y2. So by using this, I can write half m1, and m1 is 3m. So it's 3m y1 dot square plus half m y2 dot square. So this is what the kinetic energy. Now, by this kinetic energy, can we write this in a matrix format? Obviously. So it's very easy to write. It's 3m by 2 and 0 again 0, and it's obviously m. Okay, by 2. Clear? Okay, instead of this, okay, just take this as m by 2. Now the problem was like instead of this m, this can be 2m, 3m, then we will just adjust them. Okay, now if there is m, the matrix format for kinetic energy is look like this. Now come to the potential energy. So potential energy is first this one. We talk about the first one, so it's half k y1 square. And if we talk about the second one, then it's half k y1 minus y2 square. Okay, because this spring, second one, is pressed by 3m and stretched by m. That's why there's a difference in the spring is like m y1 minus y2. Clear? So we will see what will be the matrix format for this. Let's expand this. So it's half k y1 square plus half k y1 square plus half k y2 square minus k y1 y2, k y1 y2. So this obviously become 2 times. So this is k y1 square. Fine. And half k y2 square. And this, can I write this as k by 2 y1 y2. So from here the matrix format for potential energy is going to be it's k, it's minus k by 2. Clear? Again minus k by 2, then so final one is k. So this is what the format. We have v, we have t. Can I write this? The v omega square t is going to be 0, and for this format we will get the angular frequency. If I use the concept of v square minus v minus omega square t 0, then the matrix format will become like this: 2k minus 3m omega square minus k k minus 2m, it's sorry not 2, it's simply m omega square, which is equals to 0 if we solve the determinant then we got this as the equation. Just solve it. It's going to be the 2k square minus 2mk omega square minus 3mk omega square plus 3m square omega 4 minus k square equals to 0. So if we see the easiest part, then we arrange them or write it as like this. Is going to be the minus 5mk omega square plus k square equals to 0. This is what we have. Now we will apply the Dhracharya method to solve this equation. For this, it seems like omega square is equals to minus b, that is this one, plus minus root of b square, that is 25 m square k square minus 4ac is 12, it's 25, okay, so it's 25 minus 12 m square k square over 2a, so it's 6m square. Now just solve this. It's 5m k plus minus, just solve this. It's going to be the root of 13 mk over 6m square, or what we can say 5 plus minus root 13 k by 6m. Okay, so one we have frequency. If you want to write it as see, one is 5 minus root 13, which is nearly 3.6. So omega is simply root of 5 plus minus root 13 by 6 m by k. Okay, so this is what the angular frequency. Sorry, this is simply the frequency, not angular frequency. This is the frequency we have. This is the problem we have.